Hello, as we planned, this is lecture 3, the first part of chapter 2, and today we're gonna talking about three sections here. The first one is about the basic concepts of probability, and then second, which is the most important, I think, is the so-called probability rules. And then in the third section, we're gonna talking about applications of the probability rules. So those three sections are adapted mainly from chapter 2.1 and 2 sections, okay? But we are going to skip the 2.1.5 subsection, which is about probability distribution. We're going to leave that part to chapter 3. Just a little bit about introduction about the probability. So this term has been used a lot in our daily lives. People often talking about the probability as what? For example, like what are the chances that the Royals gonna win this weekend, right? And right now, we may think of the question like when the Kansas Chief is gonna win in about 2 weeks. What is the chance, right? So what is the chance of snow tomorrow? What is the chance that a patient responds to a new therapy? So whenever we talk about the chance, we talk about possibility, talking about likelihood. Those terms are kind of almost equivalent as this word probability. So formalized concept and terminology around probability is essential for better understanding probability. So how to define a probability kind of rigorously in statistics? We start with a so-called random experiment. What is random experiment? Random experiment is a action or process that leads to one of several possible outcomes. It usually satisfies the following two characteristics. Number one, we do not know any of those outcomes before the experiment begins. Sometimes we have to wait until the experiment ends, right, to get to know the final result. The diversity of the outcomes is due to uncertainty. So uncertainty got to be addressed in this process or this action. For example, if we flip a coin, we know it's gonna get either head or tail. If we flip many times, then we know we're gonna get heads and tails. And the same thing for roll a fair die. We know we're gonna get the face value one of the 6 numbers, like 1, 2, 3, 4, 5, 6. Here, uncertainty is addressed like what? Before you finish the flipping or the rolling, you do not know what you're gonna get, either head or tail, either 1 or 2 or 3, etc. That's the what we mean by random experiment. So random experiment is random, okay? This is very important. After we know the random experiment, then the probability of a outcome is the proportion of times the outcome will occur if we repeat this random experiment infinite number of times. But most of the time, we would just say many times. So here, probability is kind of like a frequency, right? But of course, it's the proportion. If we flip the coin 10 times and then we get 5 times as heads, then we would say the probability of heads is going to be 5 out of 10. That's what I mean by proportion of times. Here, probability is a numerical value that measures the likelihood that an event occurs. The value of the probability got to be 0 and 1. Here, 0 means impossible, and 1 means definite event or certainty. So if a fair coin is flipped or fair die is rolled a infinite numbers of times, what probability would that lead to? In the reality, it's kind of hard to flip a coin for infinite number of times or roll a die for infinite number of times, but it can be easily done in computer. Here, I did this simulation in R. From this chart, we know we flipped the coin how many times? We got 5,000 heads and 5,000 tails. The total is going to be 5,000 equals 10,000, okay? We flip this coin 10,000 times. And then, not surprisingly, we get half as heads, half as tail. That's what we mean by 50% of the time. So here we could say the probability of heads, or you say probability of getting heads, is 50% or 1/2. So is the probability to get tails. How about roll a die? I use this simulation to recall the whole process, right? If we roll the die from 1 time up to 100,000 times. Take a look at the very beginning, even around like 1,000. The proportion to get 1 here, ruling on 1, is ups and downs, right? Because, if we flip 10 times, pretty much like a 40% the chance. You roll the die 10 times and then you get the 1 4 times. Pretty much like a 4 out of 10. Here for 100, yes, pretty much you reached what? This 1 out of 6. So this is about this number, okay, right here. But you still see up and downs, right? If you roll over 100 times. But whenever reaches right here, actually it's already here, then this is pretty stable. You see right here? That's exactly what we mean by if we roll a die infinite number of times. Here, this infinite number is kind of like 100, right? Infinite number, in the real life, we do not have infinite number. We just say this number is big. It's very big, right? For example, like here, 100,000. But actually in this case, 10,000 is big enough to get this 1 over 6. These two simulations will serve purpose of kind of the definition of the probability. So what is the probability to get ahead? Flip a coin. Then if we flip the coin for 10,000 times, then we get half of the time heads, half the time tails. Then this probability exactly the chance of to get the heads or tail as 1/2. And here, if we roll a die many times, what is the probability to get a 1? Actually, it's 1 out of 6. After we define the probability, then it's very natural to figure out the probability for any outcome, any events. Here, first we need to construct a notion of so-called sample space. Use that two simulations, we can get the probabilities for the two outcomes there, right? But as we know, for a general random experiment, they could have all possible outcomes, right? So first, we put all these possible outcomes as a set. Here we call that sample space, denoted most of the time as capital S. We put all the sample possible outcomes together as a set. For example, roll a fair die leads to 6 possible outcomes, right? Another example here is also close to our life. It's like end of the semester, you're gonna get a grade, either A, B, C, or D, or F. Of course, here I wish everybody of you get the first one, okay? I wish all of you get A. If we put all of the possible outcomes together as a set, that's what we mean by sample space. After we know what the sample space is, sample space basically just lists all the possible outcomes of a random experiment. But sometimes, our interest is in the event, which is the connection of outcomes. Basically just several outcomes. Obviously here, an event is a subset of the sample space. For example, like we roll a fair die leads to an even number. So even number basically either 2, 4, or 6, right? So this is an event, right? Event to get an even number. Also for the grade, I define the event as to get a passing grade. You can pass this course, then basically you either get an A, B, C, or D. This is a subset of the whole sample space, which is 6 numbers, right? Is also the subset of the whole sample space, A, B, C, D, and F. Events can be referred to by letters. We can use a letter to denote an event. For example, we can use the event A is the event of rolling a number smaller than 3 on a die. Then we can define A as 1 or 2. And then we can just say, instead of rolling a number smaller than 3, use these long names, we just say event A. So this is just for the convenience purpose, okay? Just name the letter. After we know what an event is, then we need to consider the relationship of the events. This is kind of like a math. Think about the math, right? At the very beginning, in the elementary school, we learned math started with like 10 numbers. From 0, 1, 2, up to 9. We try to augment those numbers by doing what? By doing operation, plus, minus, multiplication, and division. Here is the same thing. After we defined a sample space, and then we know the whole thing is the sample space, those outcomes out of a random experiment are kind of building blocks, right? They're building the whole sample space. But our interest most of the time, those building blocks, outcomes, they form also not the whole thing, but part of it, right? As events. After we have the events, then it's very natural to think about the relationship of those events. The first one and the foremost one, I think, is so-called two events outcomes are called disjoint or mutually exclusive if they cannot both happen at the same time. The events and outcomes are closely tied to the random experiment, right? We got the outcomes out of random experiment. So if these two events cannot happen in one time, then those two events or outcomes are so-called disjoint. Graphically, it's very intuitive. For example, if we roll two dice, right here, the event A, we could define, we got a 1 and 2 right here. This is event A. And the event B as what? We get a 4 and 6. These two events you cannot get at the same time, right? You can either get a 1 and 2 or 4 and 6. Think about event D, which is 2 and 3. Then the event D with the event A, they have a 2 overlapped. So here we say event A and B are disjoint or mutually exclusive, but event A and D are not because they have an overlapped part, right? So here overlap means what? Happen at the same time. Disjoint means no overlap. That means they cannot happen at the same time. Now we could define the probability for any outcomes or events by first start with to define the probability for the outcomes of any outcomes of a sample space. After we know the disjoint and the mutually exclusive notion, we know a sample space is a list of what? Exhaustive and mutually exclusive outcomes. Mutually exclusive outcomes, that's very natural. What do we mean by exhaustive? Exhaustive means what? Because that's the definition for the sample space, right? List all the possible outcomes should be in that sample space. Suppose here the sample space has k outcomes, which are denoted as O1, O2 up to OK. Then the sample space is this, right? Not surprisingly. And the probability of each outcome we could denote as the POI. We know this probability is a number between 0 and 1. Could be 0, could be 1, okay, because this equal sign. Also, if we add all these k values together, you would get a 1. As long as these two conditions are satisfied, we would say this is a valid probability definition. Back to the die rolling experiment. We know the sample space has 6 outcomes here, and if the die is fair, then what's the probability? Because if die is fair, the chance to get each of these 6 numbers would be the same. And then we know if we add these 6 probabilities together, you will get 1. 6 equal numbers sum up to 1. What is this number? 1 out of 6, not surprisingly. So here we just use, say, probability to get I as 1 out of 6. This I could be 1, could be 2, could be 3, 4, 5, 6. After we define the probabilities for all the possible outcomes under a random experiment, then how to define an event, the probability of an event? Because we know event is what? Event is a connection of outcomes, right? Most of the time, more than one outcomes. To be honest, in the real life, whenever we're talking about the probability, it's really rare to only think about the probability only just one outcomes, okay? Sometimes they're gonna be a little bit more complicated like an event. So the probability problems often deal with events. So these events are connections of outcomes from the sample space because we could list all the probabilities for each of the individual outcomes, right? We could figure out the probability of any event. For example, roll a die. What's the probability get an even number? And we know for even number, you're either 2, 4, and 6, right? And then we know the probability for 2, 4, and 6 all are 1 out of 6. That's how we got 3 out of 6. But most of the time, it's more convenient to go from event to event directly. That's called event operations. It's like a math, right? We're talking about the numbers, but only 10. Right, 0, 1, 2, up to 9. But then we could use operations of numbers. The first operation for events is so-called union. Okay, union. We use diagrams to help us to understand what union means. sample space S, capital S, with a rectangle here. Okay, and the two circles represent events A and B. So A here, B here. What is the union of A and B? Union of B means all outcomes in A or B. Okay, we gotta pay attention to this word OR, and we denote it as a union B. So this sign actually is like a cup. Actually, in R, that's how you get this one. Okay, you just use this one as use cup, CUP in R to get this sign. Okay, we use OR means what? A union B, just basically you put these two together. This union has three parts. Is A, B, and both, right? So this is A, and this is B, and this is both in the middle, the overlapped part. Okay, together is the whole thing. Okay, what I mean by union? So union is pretty much like what? Like addition in numbers, right? You just add these two events together. Of course, this we need to put a double quote in the add, because here is not really add, right? Because from the chart you can see that. The second operation is so-called intersection of two events A and B. All outcomes in A and B. There's AND. And the sign as intersection, this sign. This is like in R, we put as cap. So the proportion in the Venn diagram is right here. That is included in both A and B, this overlap. So exactly here. Okay. Right. That's A intersects B, or you can say the intersection of A and B. The third operation is called complement. Complement of a event A, all outcomes in the sample space that not in A. Not in A. How we're going to do that? Because this rectangle is S, right? Now we have a circle, that's event A. So this red circle is A. So the red part means anything in A. But outside of this red circle is this light blue. They are not in A. That's why I put it as a complement. Okay, we use this sign, A subscript C. That's complement. So this complement is kind of like the subtraction, right? You know, for the whole sample space S, we subtract this A, and then the remainder is a complement. Or you can say A and its complement will be the whole sample space. That's very logical, very natural, because think about the event, right? Event like A here. What do we mean by event? Is a collection of the outcomes. And the sample space has all the possible outcomes. The event A is a subset of the sample space. Now for an outcome, you're either in A or not in A. Okay? There's no third choice, right? Right here. After we know those event operations, we could apply the probability rules to define the probabilities for this kind of events, which are not directly from the sample space, but from the operation of the events. For example, if we know AB represents two disjoint events, right? What is the probability for their union? Right here. And we know A union B is still an event, okay? Right? What is the probability for this event? We could go back directly to the sample space, but here we don't need to. As long as we know the probability for A and B, then we just add these two probability together, and we know this probability is going to be the probability of the A union B. For example, the die rolling example, right? And we define the event A to get either 1 or 2. Roll 2 dice. And the one die is 1, the other die is 2. And then event B as we get 4 and 6. And clearly we know these two events are disjoint, right? They could not happen at the same time. If you roll 2 dice, you could get 1, 2. You could get 4 and 6. But you could not get both at the same time. That's the idea. Then what is the probability of A union B? So A union B, basically, by this rule, we just say A, probability A plus probability B. And what is the probability of A? Because you get 1, 2 out of 6 numbers, that's 2 out of 6. The same thing for B. together, we get 4 out of 6. This is by the probability rule. But think about what is the union A and B? Union A and B basically is what? You put 1, 2, 4, and 6 together. This is also an event, right? This event is composed by 4 outcomes from the sample space. This 4 out of 6 does make sense, right? Intuitively, this makes sense. The probability rolling on a 6-sided die is 4 out of 6, right? Generally, if you have k disjoint events, A1 up to AK, then the probability that one of those outcomes would occur is right here. We just add the probabilities for the individual outcomes together. Of course, this is only for disjoint events, right? What if they are not disjoint? For the general case, suppose, we can start with a poker game. So suppose we are interested in the probability of drawing a diamond or face card out of here is all, okay? Out of a standard 52 card deck. We have 2 events. One is to get a diamond, right? This is kind of like A. And the face card will get B. So this is A or B. This is definitely the union. So from this chart, we know diamond cards 13, right? Right here. And face cards 12, okay? So diamonds, we get 13. And the face cards, we get 12. We have 3 cards overlapped. Both are diamonds and face cards, right? Diamond J, Q, and K. So here, we could not say the probability to get diamonds or face card as the probability A add the probability B, okay? Because if we add this together, you get what? You get like 25 out of 52. But in the real picture, you can see we got 3 cards overlapped, right? Those 3 cards, if you count as 25, then you double count those 3 cards. But it turns out we do not have that many 25 cards, okay? We only have 25 minus 3, which is only 22. In this case, these 2 events A and B, they are not disjoint. They are not mutually exclusive. They are overlapped with those 3 cards here. That's why we could not use this the sum of these 2 probabilities as the probability for the event of A union B, A or B. Then what should we do? There we say just right here, right? We got this one, and for this diamond and the face card, that's exactly what? Intersection, okay? This is A, this is B, A union B, right? So turns out we can easily correct it by what? Subtract the overlapped part. This overlapped part from this chart, you can see if you put the probability A as 13 out of 12 once, right? And then if you say the probability of B is 12 out of 52, it counted again. So this is exactly what we mean by double counting. How can correct this error? We just subtract this part. Then 22 is the right one. Okay, so generally for 2 events A and B, how can we get the probability for the A union B? We just add the probability of A and B together, subtract the probability for overlapped part. Of course, if A and B, they are disjoint, basically we say A and B intersection is empty set. Okay, this sign is empty. Probability of A intersect B, that's basically empty, nothing, right? And here nothing, we could just use the probability as 0. So just minus a 0, okay? So in this sense, the disjoint case, right? This one, A union B equals PA plus PB is just a special case of this one, okay? It's a special case. What is the special AB? Disjoint. All right, now we're talking about the so-called complement rule. Complement rule, so we are first we start with the example. So we roll a die, okay? So we define the event as to get 2 or 3. So the complement of D represents all the possible outcomes because, as we roll the die, we could have all these 6 possible outcomes, right? Now event D is right here, 2 and 3. So this whole thing is the sample space. And then we have the event D. And then for the rest of these 4 possible outcomes, they are not in the event D. That's D complement, okay? Right? 6 possible outcomes, split it as D, event D, and D complement. And then we want to know what is the probability of D complement. So in this case, we could just say, what is the event of D? D is what? Probability 2 out of 6, right? And for D complement is 4 out of 6. Have you ever noticed that if we add these 2 together, what do you get? We got a 1. Actually, generally, this equality holds, right? We say the complement of event A is denoted by A complement. We already know that. And the event A and its complement are mathematically related. How? The sum is 1. So here, you could also know that what is the probability for S? The whole sample space actually is 1. If we know the sum of the probability of A and A complement is 1, then we could use the probability A denoted as 1 minus complement C. But most of the time we do this way, okay? What is the probability of the A complement? Just 1 minus the probability of A. We're talking about addition rule, complement rule, this is the second one. Now we're talking about conditional probability rule, actually. Yes, we can use a rule here, but since this one is a little more complicated, we do not put it as simple as a rule, right? The intuition of the conditional probability is very straightforward. If we consider the height in the US population, the average height, the probability randomly selected individual in the population is taller than 6'4". 6'4" is very tall. If we just go, for example, we go to the street and randomly select a person, or you just go to the street and you meet a person, what is the chance to that person to be at least 6'4"? That chance, I would say, is not that high. But think about if you go to the NBA players, you only consider the NBA players, the chance to get to see a person with the height at least 6'4" is much higher. So suppose you know that the individual is a professional basketball player, the probability the individual is taller than 6'4" is much higher. So think about these two cases, okay? A is just a ordinary American. B as NBA players. Seems like you know that person is a NBA player or not. That change the probability of that person to be taller than 6'4". That's the idea. We could have another examples like most of you will, after graduation, gonna find a job, right? The chance to get a job, to land a job with a degree and without a degree is so different, right? Otherwise, you won't be here to get a degree. As we all know, with a degree, the chance is much higher to get a job. Also the same thing, if you have more work experience, you get a higher chance to get a job also. Those kind of conditions, right? The degrees, the working experience, they kind of work as the condition which drives up the probability of the event. The conditional probability of event A given the second event B is the probability of A happening knowing that event B has happened. We denote this conditional probability of A given B as this way. And we pronounced as probability of A given B. This bar, we pronounced as, this vertical bar pronounced most as given. Okay. Whenever we're talking about the conditional probability, we got at least have 2 events. Here A and B. And the order is like this. The condition part, which is after the vertical bar, the B event, occurs before A. You first get a degree and then try to find a job. You have worked in the job for several years, accumulate a certain amount of experience, and then you try to get a better one. Okay, it has this kind of order in it. That's why we say B happens before A. Like toss a fair coin 3 times, let A be the event that exactly 2 heads occurs. Okay, and then B is the event that at least 2 heads occurs. Okay, we have 2 different events. A means exactly 2 heads occurs, because if you toss the coin 3 times, B is at least 2 heads occurs. Now we're talking about conditional property of A given B. What does this mean? Condition B occurs before A. So event says at least 2 heads occurs. The B happened. Under this condition, what is the chance exactly 2 heads occurs? Because we know for the B, at least 2 heads occurs. We could have 2 heads occurs. We also have 3 heads occurs, right? Here, the conditional probability of A given B is the probability have exactly 2 heads among the outcomes that at least 2 heads. And then what is this probability? So here, conditional on B means that the sample space consists of what? 4 possible outcomes here. This is 3 heads, and the last one has 2 heads, right? For example, like the first 2 heads, and the first time you get a heads, the last time you get a heads, and then the last 2 times you get heads. But anyway, at least 2 heads. Among these 4 possible outcomes, exactly 2 heads, we have what? 1, 2, 3. 3. So this conditional probability is what? Is 3 out of 4. So this example gives us a completely picture of conditional probability. First, how to define it, right? Second, how to get it. And from this example, we know conditional probability is real, right? Because 3 out of 4. And some of you may wonder, does this conditional probability really work? To answer your question, I may give you a question. Think about what is the probability of A then, in this case. Think about for the probability A, exactly 2 heads occurs, right? Exactly 2 heads occurs, flip the coin 3 times. What are the possible outcomes here? For the conditional one, we say 4 possible outcomes. But if we only consider event A without conditional B, then the possible outcomes would be what? Other than these 4 elements, 4 outcomes, ch2, th, we have, this is 3 h's, 2 h's, we could have 1 h's and 0 h's, right? 1 h basically means what? With that, you switch this one, 2t, 1h, 2t, 1h, 2t, 1h. We add 3 more. And then with 0h, that means you 3 times always get what? Get tail. So together, this one we have how many? We have 8 outcomes in this sample space. Now with exactly 2 heads, which is 1, 2, 3, right? Exactly 2 heads. So here, the probability of A actually is 3 out of 8. So you see, numerically, the conditional probability of A given B is 3 out of 4. But the unconditional probability of A is 3 out of 8. They are so different, right? Now, generally, we could define this probability as what? As this way, okay? The conditional probability is defined as the ratio of the probability of A intersects B over probability of B. Of course, to make this definition valid, this probability of A got to be greater than 0, cannot be 0, right? Because we know 0 as a denominator is going to be a problem. So back to the die rolling example. Here is A intersects B. At least 2 heads, exactly 2 heads, that's exactly 2 heads, right? At least 2 heads, at least 2 heads. So at least 2 heads, that's exactly the probability of B. This is at least 2 heads. And exactly 2 heads, 3 possibilities. That's how you get it. 3 out of 4. To understand this formula better, we could just use a chart, Okay, I put right here, okay? The probability of A given B we defined as the ratio of the probability of A intersects B over probability of B. Now think about it. Where's the part of this A intersects B, right? As we talked about before, this is the overlapped part. What is B? B is this whole circle, purple circle, okay? This one. Think about condition probability. This condition B, right, occurs first. If B occurs, what is the influence of B on A? If B already occurs, the only possible effect or the influence of B on A is on this overlapped part, because this part is also part of A. So what does it mean? For the other parts, for example, rest of this overlapped part of B, for these purple ones, they also occur, right? But they're not going to affect the occurrence of A at all. Among the whole B, only this overlapped part works or affect A. You can see this ratio makes perfect sense, if we explain it in chart like this. This is very important, okay? So for the conditional probability, how this is defined, if you find it really hard to understand, I would recommend this picture. Think about why this conditional probability is defined as this way. Okay, see, B has occurred first, right? And then among the whole B, only the overlap part would affect A, right? Because that's exactly the conditional probability idea, right? If the B has nothing to affect A, then we do not need to consider the conditional probability of A on B, right? All right, with the conditional probability notion, we could just have a general multiplication rule. What does it mean? You see, multiplication, we could understand as the intersection, kind of like that. If we want to get the probability of the event A intersects B, get the probability of A given B, the conditional probability, and then multiplied by the probability of B. How do we get that? Actually, this is exactly from the definition of the conditional probability, right? We talked about just now. We just move this one. That's how we get it, right here. Unlike the previously mentioned multiplication rule, this is valid for events that might not be independent. What does this mean? This means later we're talking about independence, but here this is the multiplication rule, okay? So we could just say, what does the multiplication rule say? The multiplication rule says we could just use this rule to get the probability of A intersects B, as long as we know the conditional probability of A given B and probability of B. Because we just multiply these two probabilities, we can get the probability of intersection of A and B. The last rule is called the Bayes rule. The Bayes rule, the simplest form, right here. Probability of A given B equals still a ratio. We put a B in the bottom. For this part, is very close to what? Is very close to the conditional probability, right? But actually, you're right. That's exactly the conditional probability is right here, right? A given B. But now we go one step further, because by the multiplication rule, we know this probability of A intersects B equals the multiplication of the conditional probability B given A times A. Some of you may say, oh, we just repeat this again? Is this a reasoning circle? Actually, they are different. We start with A given B, okay? That means B occurs first, A occurs next. But on this right-hand side, we have switched B and A. Now B is in the front, A is in the second, okay? So A becomes what? Condition now. That's the amazing part of the Bayes rule. That's why Bayes rule sometimes we also has another name. It's called inverse probability rule. Okay, why is it called inverse probability rule? Because we start with A given B. Okay, and then we end up with B given A. We have reversed A and B. Now we need to investigate a little bit about this denominator of the Bayes rule, which is the probability of B. Most of the time, this probability B is kind of complicated. It's not given directly. Then we need to calculate this one. How can we do that? But actually, we could use a very good chart to explain it. Okay. For example, here is S, the rectangle. Okay. Now we have a B. Okay, this is right there. We want to know the probability of B. How can we do that? If we know there is an event A, for example, what is A? A is here. This right here is A. This part is A. The whole thing part is A. Now, what is the other half which is not in A? That's exactly A what? A complement. For the complement rule, we know that AC and A complement and A, if we union them together, that's exactly S, right? Because if we put A and A complement together, that's exactly S. But for the individual event in the sample space S, you can see not only S is split between A and A complement, but for any event like B in this sample space is also split by what? A complement and A also. That's why probability of B is the sum of the probability of B intersects A, which is this part. And B intersects A complement, which is this part. Because the intersection, right, we can use the multiplication rule again to put it as the multiplication of conditional probabilities times A. But here you gotta be careful. One is conditional on A, the other one is conditional on A complement. Now we put this probability of B back to this formula again. That's why we get the last one, okay? So this is the completed one, which says you can see how nice this one is, right? So we start with the A given B, and then we end up with B given A and B given A complement. The whole idea of the Bayes theorem or Bayes rule is what? Most of the time, we want to know the probability of A given B. It's kind of hard. But if we use the rule, then we can switch to B given A or B given A complement. Hopefully, as long as those probabilities are easily found, then this rule is going to help us a lot. But it turns out that's true. And then we're going to explain this in a very good example in the application part. The first application is we could use the probability rules to tell whether two events are independent or not. But actually, what do we mean by independent? If the probability of A and B occurs equals the product of their separate probabilities, right? What do we mean by that? The probability of both A and B. Because as we explained, right, A intersects B means what? A and B, both A and B. That means A and B happens at the same time. If this probability is equal to the product of the probability A and B, these two separate probabilities, the product of these two separate probabilities, then we would say this A and B independent. Actually, this narrative is very intuitive, right? A intersects B, you have to consider A and B at the same time. Probability A times probability B means what? You just separate them and then multiply them together. So either way, if we end up with the same probability, that means they are equal, then we would say these two events are independent. Okay, the textbook uses a very nice example to say, roll two die, but one is blue die, the other one is green. And then what is the probability of rolling two ones? You could just roll these two dice together. That's how we got this one. With the green die and the blue die, and then together, we get a 1-1 right here, right? This part. And we know what is the sample space. If you roll these 2 die, that's exactly, you could get green as 1, for example, blue as 2, green as 1, 3, right? Like this, and then the same thing repeat for how many times? 36 times. That means the sample space has 36 outcomes. You roll 2 dice, 1 is blue, 1 is green. Okay. So what is the probability for A intersects B? Because you get 2 ones, right? That's exactly 1 out of 36. If you roll blue die and green die separately, PA means what? You roll the green die, let's put A here, B here. Column as A, row as B, okay? Then you roll the green die, you get 1. What is the chance? 1 out of 6, right? You roll the blue die, what is the chance to get 1? PB is 1 out of 6. Take a look. 1 out of 6 times 1 out of 6, that's exactly 1 out of 36. These two numbers, you see, they're exactly the same thing. Now you see here, you roll blue die to get 1, roll green die to get 1, A and B, these two events, right? They are independent. So here, independent has a very intuitive narrative. Either you roll these 2 dice separately or together. The chance to get 2 ones, the same. 1 out of 36. This is so nice, right? Think about this example. This is a very good example, okay? If we know the notion of independence right here, and together with the multiplication rule, so as long as this is satisfied, they're going to be independent, right? Combined with conditional probability notion. So conditional probability notion says what? The PA given B is A intersects B divided by PB. And if they are independent, right, we put this one here. So we replace this intersection, probability of A intersection B, as the probability A times probability B, right here. And then divided by probability, this one gets cancelled. And then only A left. That's why if the conditional probability of A given B is the same as the probability A, then we say A and B independent, right? Knowing A offers no information about whether A occurs. The other way around is the same thing, right? The same idea. P given A. By the definition, we have B intersects A divided by PA. Oh, by the way, if we say A intersects B and B intersects A, they are the same thing. Okay, if we switch, they should be the same thing. Does not really matter. Okay, so in this case, again, PB times PA divided by PA, and then PA gets cancelled, which is PB. That basically says the conditional probability of B given A is the same as the probability of B unknown without the condition A. That's another way to say A and B independent, right? See, independence idea is great, okay? Especially we just defined in the probability rules, which makes it very clear cut. And independence is very important in statistics also. So please make sure you understand it. Now, the last, we're going to talk about the application of the Bayes rule. We're talking about diagnostic testing, okay? 4 events here. We could as example, like we want to use a test to test the COVID-19, right? That's a perfect example for diagnostic testing. So we have disease present as D, and disease absent, that's D complement. That's exactly opposite to each other, right? And then we have the test result as positive and test negative. We could use T and TC, but we use this one notions. These notations are better because they are used in the real life. So you know this is the idea, right? These are opposite to each other. Okay. The following measures are all characteristic of a diagnostic test. So first, we're talking about the sensitivity. What is the sensitivity? Think about the COVID-19 test, right? We want to know whether the test is sensitive or not. Basically, it says whenever there is a COVID-19 and the test what? Detects it, right? Here is the same thing. Whenever the disease is present, what is the chance for the test is positive, right? We could use the probability to define this notion very nicely. The same thing for specificity here. Whenever disease is not there, and the test should be what? Negative. These two are very natural ones, right? But we have some so-called false negative rate. What is the false negative rate? The disease is there, but the test is negative. And obviously, you know this false negative rate exactly the complement of the sensitivity, right? Because sensitivity means when test is there, when the disease is there, the test detects it. So that is 1 minus that. That's exactly the what? Complement rule. And the false positive rate. False positive means the disease is not there and the test is positive. Is exactly complement to the what? Okay, right here. So these four notions are very important in diagnostic test. And then talking about a little bit another term which is called positive predictive value, PPV. We simplify as that. In probability, in statistics, the probability can be easily defined as what? The test is positive, right? You go to the COVID test and the test is positive. And then immediate question is, do I really have the COVID-19, right? This is a very natural question. That's exactly the PPV is about. Our question now is, if we know all these 40s, right? Sensitivity, specificity, false negative rates, and false positive rates. And then we want to know, what is the PPV? Because this is natural for a test. Because most of the time, we want to know reliability of this test. How the test is reliable. Reliable basically has two meanings, right? One is the so-called sensitivity. When disease is there, your test is positive. But it's another one, when test is positive, is the disease really there? So this is kind of opposite, okay? Now we can use the Bayes rule to do it right here. We want to know this PPV, okay? Right? When test is positive, is this test really right? Or equivalent to say, is the disease really there? That's exactly most of the time in the real life, right? We want a second opinion. This is exactly the idea. By the definition, Bayes rule. Actually, the first step is actually this is definition of the conditional probability. From here, that's exactly what? The Bayes rule, right? And then the last is right here, Bayes rule. So here, the Bayes rule tells us we can go directly as from the first to the fourth. And then we just replace probability with their names. There's a new one, which is the prevalence. Prevalence is the PD, which is the what? The chance of this disease. So most of the time, this one should be available. This one is available, this one is available, everything is available, then we could get this one, okay? PPV. So the PPV is very important, to evaluate the test. This is the chart, okay? Now we do a little bit of kind of like summary with this chart here. We have the D and the C and the DC, right? So whether have the disease or not, whether the disease is present or not. So this whole is S. And then we have T plus as actually it's not a circle, it's an oval, okay? As a T plus, test positive. And then we want to get the probability of D given T positive, okay? So test positive, we want to know whether the disease is there or not. That's exactly the PPV, right? We could just split this oval, this T by two parts. One is in the D part, the other one is in the complement part. That's exactly here for this part, right? And here for this part. We split the T into two parts. That's exactly the bottom term here. Among these two parts, only this part is gonna affect the D, right? That's why we put this on the top. This Bayesian idea, Bayes rule or Bayes theory, that's still a conditional probability, like we have it right here, right? PPV. For this conditional probability, right? But this condition is kind of complicated, right? Because you have the intersection. That's why we use multiplication rule to say, to get the T positive as a D is what? Is easy to get, okay? This part right here, the same thing. Yes, I put a circle here. And then plus, there's another one intersection, which is TD, T plus given the complement and the P D complement. Okay. So I hope this chart will help you to understand what the Bayes rule is about, especially in this very specific example right here. Think about why do we need this kind of notion here? Because we know most of the time for a test, right? We know this test, if the disease is there, what is the chance for the test is positive? Because most tests are going to specify that one. But the PPV is considered a different notion, okay? They want to know if the test is positive, what is the chance for the disease is really there, okay? So we could use the Bayes theorem to get this value.